Welcome to EnfinityCast, where we explore the science and technology shaping our future. I'm your host, Elion Quanta. Today, we're tackling a concept straight out of science fiction, building a star on Earth. We're talking about nuclear fusion. And to help us unpack this monumental topic, I'm joined by my co-host, Roy Vale. Welcome, Roy.
Great to be here, Elion. It's a topic with an almost mythical status, isn't it? The promise of truly clean, virtually limitless energy.
Exactly. So, for our listeners, let's start there. When we say clean and limitless, what does that actually mean in the context of fusion?
Well, the fuel itself is the key. Unlike nuclear fission, which splits heavy radioactive atoms, fusion combines light elements, like isotopes of hydrogen. The primary fuel, deuterium, can be extracted from seawater, and the other, tritium, can be produced inside the reactor. So the fuel supply is immense. And crucially, the process doesn't produce long-lived radioactive waste or greenhouse gases. The main byproduct is helium, which is completely harmless.
An endless supply of fuel and no carbon emissions or toxic waste. It sounds like the perfect energy source. So, what's the catch? Why don't we have fusion power plants on every corner?
The catch is that building a star on Earth is quite literal. To get hydrogen atoms to fuse, you need to overcome their natural repulsion. This requires immense pressure and temperatures. We're talking over 100 million degrees Celsius, hotter than the core of the sun. The central challenge has always been how to create and contain that superheated plasma without it melting whatever vessel it's in.
Right, no physical material can withstand that.
So scientists have developed these incredibly clever non-physical containers. The most famous is the tokamak, which uses powerful magnetic fields to suspend the plasma in a donut shape, preventing it from touching the reactor walls. And the other leading approach is inertial confinement, which is what we've been hearing a lot about recently. Instead of sustained magnetic fields, this method uses incredibly powerful lasers to rapidly heat and compress a tiny fuel pellet, triggering a brief burst of fusion before it has a chance to fly apart.
And that brings us to the breakthrough. In late 2022, and again since then, the National Ignition Facility in California achieved something called ignition, or net energy gain. For the first time, they generated more energy from the fusion reaction than the energy the lasers delivered to the fuel target. That's a historic milestone.
It absolutely is. It proves fundamentally that the physics works. It's the Wright brothers moment for fusion energy. But, and this is a big but, it's not a power plant yet. The total energy required to power the entire facility and its massive lasers is still far greater than the energy produced. The next challenge is engineering efficiency.
So, what are the next steps? We have proof of concept, but how do we get from a single successful experiment to a grid-ready power station?
The next big step is projects like ITER in France, a massive international collaboration building a tokamak designed to produce a sustained high-energy plasma for long periods. The goal there is to solve the large-scale engineering and material science problems. We need to go from a net gain in the fuel pellet to a net gain for the entire plant. And that's a huge engineering leap that will likely take a couple more decades, so the finish line isn't quite in sight. But for the first time, we can genuinely see it on the horizon. The quest for fusion energy is shifting from a question of pure science to one of practical engineering. A fascinating and hopeful prospect. That's all the time we have for today. Thanks for joining me, Roy. My pleasure, Elion.
And thank you for listening to EnfinityCast. Join us next time as we continue to explore our infinite future.